Um, we're continuing with Ndefo Okigbo classes. Ndefo Okigbo classes. We're going to analyze frames, determinate frames that we've been dealing with beams, simply supported beams that are determinate. Now we're going to analyze frames that are determinate as well. This is lecture 6. Frames. Take for instance, we're going to analyze different types of frames. Let's start with simple frames. Simple frames like this. In this frame, when it's loaded, let's say it's loaded with a UDL. When it's loaded, it's A, B, and C. The load acts that there's only one support at A. So to get we don't know to get to calculate reaction, because the reaction is equal to the load. The load is there because it's only one support that is carrying the whole structure. So that support bears the whole effect of the load, and its reaction will be equal to the load. Now, to start, where I may say, okay, let me load this frame with about a load of about, let's say, 8 kilonewton per meter. Let's say the span of the frame is about 6 meters. Let's say 6 meters. So the span is 6 meters. Let's say that the height is about 5 meters. 5 meters. Now I am to, of course, get the reaction, which is already known, get the bending moment on this structure, and also get the shear force. We can also get normal force here because there is tendency of normal force in this area. So let's start with the bending moment. We are starting from point C. Okay, the reaction is the load. So reaction at A is the load, because it's only one support. So, and the total load, because the load is 8 kilonewton per meter, 8 kilonewton per meter, and there are 6 meters. So the total load will be 8 times 6, which is 48 kilonewton. 48 kilonewton load. That is the reaction at A. There's no reaction at C because C doesn't support. There's no support at C. So since we're going to the reaction, now let's get bending moment. Now I said we should start bending moment from where it is minimal, that is at point C. We start from point C. Start bending moment where it is minimal, and here is C, because C, bending moment at C is 0. That's the minimal I'm talking about. So I now start. I said that when you want to start the bending moment at C, M at C is equal to 0, because there is the load. There's no distance to give the load full value, to give you a bending moment. So after C, we now move. Since we are starting from C, we put the bending moment that we're trying to get at any point. Let's say at point B, or if we want to here, let's call here point E, the middle before B. So if I want to get at this point E, the bending moment, I have that ME. Now, if I want to do the way from first principle, I'll just say that ME turning this way, ME turning towards the B where I started from point C. I say it's positive. Any other one I guess is negative. So, and the load, look at the line of action of the load, which will turn the same way with the moment, which means it will be plus the 8, the distance from B to C, from C to E is 3, half of the space. So 3 meters. 8 times 3 squared, 3 times 3 over 2. 8 times 3 squared over 2. So it's equal to 0. ME. Moment at E is equal to, this is 4, 2 cancel it, 4 times 9, which is 36 kilonewton meter minus for that matter, because it has left the sign of equality to minus. That's the moment at E, moment at point E. If I'm to get the moment at point B, I move straight. Let me not walk straight from first principle, since it has been understood. I just say M at B is equal to 8 times the distance is 6 over 2 minus 6 times 6, that's 36 times 4. That's 36 times 4. That gives is equal to 144 kilonewton meter. Minus 144 kilonewton meter. So that is the up to point B. Now, if I want to get bending moment along BA, I will still take, because bending moment is force times perpendicular distance. To get the bending moment along point E, it will be, so the bending moment at, well, for instance, at anywhere, let's say here is, let's give her here F at this point. At point F is a mark F. It's the same thing. It's 8 times 6 over 2. That is 8 times 6 as a bunch of load. Create a moment from the half of 6, half of the distance. That is the area that is, which is also minus 144 kilonewton meter. That is the area, the length, half of this length, the force. If you watch the line of action of the force, look at the arrow I'm drawing. The line of action of the force is parallel to BA or BF. Is parallel to it. So it cannot multiply the distance BF or BA to get moment, because that distance BA or BF is not perpendicular to the load. The distance that is perpendicular to the load is BE or EC or BC. That's the ones that are perpendicular. So to get moment along, so the moment at A, M at A is equal to the same thing. 8 times 6 squared over 2 minus, which is minus 144 kilonewton meter. Because along BA is not perpendicular. That emphasis, perpendicular distance. The only distance that is perpendicular to the line of action of this force, the line of action is the arrow, which I drew, the arrow. Let me say PX. That arrow is the line of action of the force. And the moment is that force, which has that line of action, times the distance that is perpendicular to that line of action. And the distance that is perpendicular in this case to that line of action is the distance BC, BE, EC. The distance BF or BA is not perpendicular. So, and we can, even when we're taking moment along BA or BF, we can't multiply with BA or BF, because B or BF is not perpendicular. The one that is perpendicular is BE, EC or BC. That's why the moment continue giving the same value as I move along BA. Such moment at point B, from point B down to A, such moment is called concentrated moment. It's giving you the same value, concentrated moment. So this is the moment in this structure, in this frame ABC. This is the moment. The first moment, the moment at C is equal to 0. The moment at E is equal to minus 36 kilonewton meter. The moment at B is minus 144 kilonewton meter. The moment at F is minus 144 kilonewton meter. The moment at A is minus 144 kilonewton meter. So we have gotten all the moments. So if I wish to draw the diagram. If I want to draw the bending moment diagram, I have the structure this way. I want to draw the diagram. The diagram will be like this. because number one is that the bending moment at C is 0. That's why it starts and it increases to E. At E is 36 kilonewton meter. That is minus. At B, it is 144 kilonewton meter. That's minus. At B is minus. Let's B. So from B now, that's the same thing at B. Look at the diagram. The same thing. Then it was uniform throughout. That's why this diagram became a rectangle. So 144 there is still 144 here. Negative is still 144 kilonewton. This is the bending moment diagram. That's how the diagram of the bending moment of that frame will appear. That's the bending moment diagram for the frame. Now, if I want to calculate shear force, here the shear force starts from C. Or if I want to start from B, that means the shear force at C is 0. The shear force at B is 8. That's the total force. That's 8 times 6. That's 48. So the shear force diagram, even at A, along B, the diagram should be like this: 0 at C and 48 kilonewton at B. At A, there's no shear force along BA. There's no shear force along BA because the member BA is not across. It's not across the line of action of the load. It's not across the line of action of the load or the force that generating shear force. It is only BC that is across the line of action of the load, or the line of action of the load that generating shear force. So what we may have in the member AB, what we may have in the member AB is normal force, which in this case is the same 48. That's normal force. The diagram will be this way. The diagram of the normal force. This is B, this is A, this is C. This is the normal for 48. 48 kilonewton. That is the normal force on BAB. That's where normal force is. So we have shear force here, normal force here. This is bending moment. So we have analyzed this frame and got all the stresses needed for this frame to be designed. So that is exactly how to get the reaction, how to get the bending moment, how to get the shear force, how to get the normal force, since there is no normal force in the frame. And where there's normal force is in AB. There's no normal force in BC. There's normal force in AB. So that is that. Thank you very much. That's the end of this.